.10 Data Structures. Note: this section is an adapted and updated version of an article submitted to ICMIC 2002. The original idea in developing PD was to make a real-time computer music performance environment like Max, but somehow to include also a facility for making computer music scores with user-specifiable graphical representations. This idea has important precedents in Eric Lindemann's Animal and Bill Buxton's SSP. An even earlier class of precedents lies in the rich variety of paper scores for electronic music before it became practical to offer a computer-based score editor. In this context, scores by Stockhausen, Kontaktens Studie 2, and USA Toward the Midnight Sun come most prominently to mind, but also Xenakis's Mycenae Alpha, which, although it was realized using a computer, was scored on paper and only afterwards laboriously transcribed into the computer. PD is designed to offer an extremely unstructured environment for describing data structures and their graphical appearance. The underlying idea is to allow the user to display any kind of data, associating it in any way with the display. To accomplish this, PD introduces a graphical data structure, somewhat like a data structure out of the C programming language, but with a facility for attaching shapes and colors to the data, so that the user can visualize and/or edit it. The data itself can be edited from scratch or can be imported from files, generated algorithmically, or derived from analyses of incoming sounds or other data streams. There's a tutorial section dedicated to data structures for .data.structures, with many examples. Here is one simple example from this series 09.sequencer.pd, with a very short musical sketch realized using PD. Graphical score. Fig. 2.10.1 A graphical score with data structures. The example, which only lasts a few seconds, is a polyphonic collection of time-varying noise bands. The graphical score consists of 6 objects, each marked with a small blue rectangle at left, and with data shapes. A black shape to show dynamic, and a colored shape to show changing frequency and bandwidth. The horizontal axis represents time and the vertical axis frequency, although, as explained later, this behavior isn't built into PD. The dynamic and frequency shapes aren't constrained to be connected or even to be proximate, but since they pertain to the same sound, their horizontal positions line up. In this example, the last furthest right object is percussive as seen by the black shape, and has a fixed frequency and bandwidth, whereas the large, articulated shape in the center has a complicated trajectory in both frequency and amplitude. The color of the frequency has no purpose, but could be used to determine a voice number to route it. Each object is thus composed of a combination of scalar values, color, aggregate position in x and y coordinates, and array values, time and envelope pairs for the black traces and time, frequency and bandwidth, triples for the colored ones. This is all specified by the user using PD's template mechanism. Here is the template associated with the graphical objects shown above. Template for graphical score. Fig. 2.10.2 The struct and drawing instructions for the score's elements. Templates consist of a data structure definition, the struct object, and 0 or more drawing instructions such as fill, polygon, and plot. The struct object gives the template the name template event. The data structure is defined to contain 3 floating point numbers named chapter Y in color and 2 arrays, one named pitch whose elements belong to another template named template pitch, and similarly for the array amp. Both data structures contain 3 floating point numbers named chapter Y and W for X, Y position, and width. In general, data structures are built from 4 data types: scalar, floats and symbols, text and arrays, whose elements share another specified template. The contents of a PD window themselves form a list. Arrays are actually implemented as a top-level data structure array, whose elements are scalars containing a single floating point number. Data structures in PD may nest arbitrarily deeply using the array and text types. For example, a collection of sinusoidal tracks from an analysis engine could be implemented as an array of arrays of pitch, amplitude pairs. After the struct object in the template shown above, the remaining 3 objects are drawing instructions, first for a rectangle with the fill polygon object, and then for 2 arrays with the plot objects. The various graphical attributes that are specified for drawing instructions may be numerical constants or data structure field names. In the latter case, the value varies depending on the data. For instance, the second creation argument to plot is the color. The first one plots pitch using the color. In this way, the color is attached to the color slot in the data structure, so that color will vary according to its color slot. The second plot plots the amp field, and the color is given as 0, which is black. 2.10.1 Traversal. PD objects are provided to traverse lists and arrays, and to address elements of data structures for getting and setting. PD has no built-in sequencer, nor even any notion that chapter values should be used as a time axis. However, a sort function is provided, which reorders a list from left to right on the assumption that users might often want to use PD data collections as X-ordered sequences. Recording sequences of events into lists and/or playing the lists back as sequences are functionalities that the user is expected to supply on top of PD's offerings, which, it is hoped, would allow those functionalities within a much larger range of possibilities to include random reorderings of events, score following, self-modifying scores, reactive improvisation, and perhaps much more. Here is a screenshot of the subpatch that implements the graphical sequence score shown above. It takes a start or stop message, and the sequencing is done in the PD sequence subpatch. It also uses the clone object to instantiate different copies of the voice abstraction, which is responsible for synthesizing each voice from the score. Score playing subpatch. Fig. 2.10.3 The subpatch that plays the graphical score. Traversal of data is made possible by adding a new type of atom, pointer to the 2 previously defined types that make up messages, numbers and symbols. Unlike numbers and symbols, pointers have no printed form, and thus can't be uttered in message boxes. Traversal objects such as pointer and get, among several others, can generate or use pointers. The pointer data type is also integrated into pipe-fitting objects such as pack, unpack, and route. The trigger object also deals with pointers. PD sequence subpatch. Fig. 2.10.4 The sequencing subpatch. In the PD sequence subpatch shown above, a first pointer object is used to traverse through the data. It first takes a traverse message, sent from the parent to set it to the head of the list, named PD data, and next messages to move to and output the next datum in the list, i.e., the next in the list of 6 objects in the score. A second pointer object is used here as a storage cell for pointers, just as float is for numbers. The center of the sequencer is the delay object, which must be fed the time difference between each event, including the non-event of hitting start, and the next. The time difference needed to set the delay object is obtained using the getTemplateEvent object with the X field. This is converted to incremental time with minus, corrected for tempo, and fed to the delay object. PD provides the get and set objects for reading and writing values from data structures. The get object shown here obtains the chapter and Y fields of the current object. The template name templateEvent is supplied to the get objects so that they can look up the offset of the necessary field S in advance for greater runtime efficiency. As we extract each of the 6 objects in the score, we must wait the delay for playing that object. Once the delay time has expired, the object's pointer is recalled with the second pointer object and packed with the pitch base value to cloned instances of the voice abstraction for that a next message is prepended to the list, which is needed by clone. Let's check the voice abstraction below. Voice abstraction. Fig. 2.10.5 The clone voice abstraction with sound synthesis. The pointer and pitch value are unpacked. The pointer value is sent to data array abstractions, which extract the pitch and dynamic breakpoints from the arrays, specified as the abstraction's argument, so it contains 2 subsequencers itself. The nesting of the overall structure of the sequencer patch mirrors the nesting of the original data structures. Let's have a look at the data array abstraction below. Data array abstraction. Fig. 2.10.6 The data array abstraction. We have to inspect the object itself to know the delay before playing it. So in the loop, we peel off the first remaining object to play and inspect the time difference between it and the previous one using this value to set the delay object. More general patches can easily be constructed which access heterogeneous lists of objects, having different templates. In this way, an arbitrarily rich personal score language can be developed and sequenced. 2.10.2 Accessing and changing data. In general, accessing or changing data is done via pointers to scalars. Numbers and symbols within scalars are accessed using the get object and changed in the same way using set. Since lists and arrays are composed of scalars, every actual number or symbol in a data heap will be a number or symbol element of some scalar. To access them, it suffices to have objects to chase down elements of lists and arrays, given either a global name or a pointer to the containing scalar. Lists are traversed in the way shown above to get to a sublist of a scalar. The get object will provide a pointer in the same way as it provides float or symbol elements of scalars. For arrays, an element object is provided which, given a scalar, a field name and a number, chases down the numbered, scalar element of the named array field. To alter float or symbol elements of scalars is straightforward using the set object, but arrays and lists can't be set by assignment. There is no suitable data type available within messages. Lists could possibly be settable by passing pointers to other lists, but permitting this would have required either automatically doing deep copies of data structures to carry out the assignments, or else implementing a garbage collecting memory management system, either of which would be difficult to realize within real-time computation time constraints. Instead, all the data hanging from a scalar is considered as belonging to that scalar and is left in memory until the scalar is deleted. The data may be changed atom by atom, but primitives are not provided, which would imply unpredictable execution times. The getSize and setSize objects are provided to access or change the number of elements in the array. For lists, an append object appends a new scalar for a given template to a list after the element pointed to. To insert a scalar at the beginning of a list, the pointer can be set to the head of the list, a formal location before the first list item. Deletion is less flexible. The only operation is to delete an entire list. There's no reason not to provide finer grained deletion mechanisms, except that it's not clear how to protect against stale pointers efficiently, except by voiding the entire collection of pointers into a list. 2.10.3 Editing. The graphical score shown above can be edited by dragging breakpoints or by adding and deleting them using mouse clicks. Also, entire objects or collections of them may be copied, pasted and dragged around the screen. Alternatively, there is an editable or computer-generate-able or parse-able text representation for the data, which may be seen or changed in a dialog window or read and written to external text files. Since the graphical presentation of data objects is determined by drawing instructions, the drawing instructions are interpreted backward to alter data as a result of mouse operations. If a given graphical dimension is controlled by a variable, that variable is then controlled by dragging along that dimension. If the dimension is constant, it can't be altered by dragging. Tricky situations can arise when the user changes the contents of templates. A change in drawing instructions can be accommodated by simply tracking down and redrawing all data objects using the template. However, changing the struct object itself make for less straightforward situations. The user might wish to reorder fields, delete them, add new ones, or rename them. When a struct object changes, PD automatically conforms the data from the old structure to the new one. Fields with the same name as previously are maintained, reordering them as necessary, and if a field disappears but another of the same type appears, the new 1s are taken to be renamings of the old 1s in order of appearance. New fields which cannot be matched in this way with previously existing ones are assumed to be new and are initialized. It can happen that two struct objects compete to define the same data structure, or that the user reads in data from a file which expects a different version of the structure, or alternatively that the struct object for existing data objects disappears. For this reason, PD maintains a representation of the last active version of a struct until all similarly named structs as well as all data using that struct have disappeared. If the user introduces a new version of the struct and only later deletes the current one, the data is only conformed to the new version once the old one is deleted. In this way, we avoid getting into situations where data is left hanging without its structure definition, or where data ends up belonging to two or more structures of the same name. The worst that can happen is that data may lose their drawing instructions, in which case PD supplies a simple default shape. 2.10.4 Limitations. When examples get more complicated and/or dense than the one shown here, it becomes difficult to see and select specific features of a data collection. More work is needed to facilitate this. There should be some facility for turning drawing instructions on and off, or perhaps for switching between versions of a template, depending on the user's desired view. There should also be a callback facility in the template for when an object is edited with the mouse, so that the user can bind actions to mouse clicks. More generally, the collection of traversal objects that PD provides is adequate to support a variety of modes of data collection and use, such as analysis and sequencing. But the patches required to traverse the data collections are not always simple. It would be desirable to find a more straightforward mechanism than that provided by the pointer, get, and set objects. The data facility, although part of the original plan for PD, has only recently been implemented in its current form. And as hopefully the user base grows, there will surely be occasions for many further extensions of the data handling primitives and the graphical presentation and editing functions.